In the next section of lessons, we're going to be talking about time series objects. There are a handful of models I want to discuss, but most importantly, we need to know how to create XTS objects as well. So in this lesson, we're going to discuss how to create and manipulate an XTS object. XTS stands for Extensible Time Series, and there are many tools that help us deal with different problems we can come across when working with time series data. Previously, we have talked about different time classes, such as POSIX CT. So we can use the system time function to get the current system time. And the class of that object is POSIX CT. Now I want you to install a package called XTS using the install.packages function. And then we're going to load it into our environment using the require function. Now creating an XTS object is simple. It requires two arguments, a data vector and a time index. So why don't we create our first simple XTS object? It's going to be 20 random numbers, and we're going to set the order.by argument to be a vector of dates. When we use the class function on this XTS object, we get XTS. And we can also look at the attributes. When we look at the attributes of X, we're given a few things: the dimensions of that object, the timestamps, which are turned into numerics, and then there are other things such as time zone. Now we can also throw in hourly timestamps. Whenever we subtract or add integers to system time, it is in seconds. So I can multiply a range by 3600 to make sure that we are subtracting hours. So instead of system date, we're going to use system time. And I'm going to subtract 3600 times this range of numbers 20 through 1. And I'm going to set a new attribute this time called time zone. And generally, the format of a time zone will say something like this: America/Chicago. Now let's talk about subsetting. There are ways to subset time series data by any time frame. We can take either a single day. So when I entered this one day as a character string into the square bracket subsetting notation, it returned only those observations which were from March 26th. We can also subset by using a backslash operator in the square brackets. And you can see with this notation, I'm going from this timestamp all the way to this timestamp. It should always be in that format. So let's talk about a couple of functions that are very helpful for XTS objects. The first is lag, which will lag the values. So if I lag X, for each observation, it's going to give me the previous observation of that data set. All of the observations get shifted forward. One timestamp is another way to think about it. That's why there is an NA at the start. There is no 0th index observation that it can pull from. Now we can set the number of lags using the K argument. So if I set K to be 5, we're going to get NAs for the first 5 observations. And then at this time, it's going to be able to pull whatever observation was 5 timestamps ago. You can even do negative lags. If we set K equal to -5, it's going to end with a bunch of NAs. Another useful function is diff. It returns a vector of the change between each observation. Now it's a little harder to see this because they're random variables. But for example, if I create an XTS object out of just the integers 1 through 20, and I did a diff on X, it's going to return a series of 1s with an NA at the start. In this lesson, we covered some of the basic ideas of an XTS object, such as how to create one, how to subset one, and a couple different functions that we will be using. Now let's talk about XTS plotting and what are called ACF functions. First, I'm going to create a random time series, and we're going to explore the lagged values. Now, when we plot a time series object, it looks different from a basic data matrix plot. Here we can see grid lines and timestamps on the x-axis. So let's revisit the lagged values. I'm going to cbind X with a lagged version of itself. A great way to see the relationship between these lagged and current values is to use lag.plot. Now this looks messy, and it's mostly because we have been using random data, but it shows you the differences between current and lagged values and how they evolve. Let's see how it looks when we use a cumulative sum of the series. I forgot an M in the cumulative sum function. So here is the cumulative series. Now let's see what a lag plot looks like on this cumulative series. Now we see more of a developing pattern. We can see that from each observation to the next, there's a general trend upwards, just as we saw in the plot of the series. Around the 15th observation, it starts to turn back and turn downwards. Another important plot when analyzing time series data is called the autocorrelation function. This will give you a plot of the correlation at every available lag in the time series. So let's create a new random series that's a little longer than our last one. To see the ACF plot, it's very simple. Just use the ACF function. Now this plot tells us if there are correlations among the lags. Usually when we are creating a time series model, such as an ARIMA model, we want to select the number of lags that cause all of the lag correlations to drop below the blue threshold. Now the lag correlations are all below 20%, which is a good indication that there is no autocorrelation in this series. Now, of course, you'll notice that the 0th lag is 1. That's because the series is perfectly correlated with itself. Now, what if we use the ACF function on the cumulative series of that random dataset? Now we can see a concerning pattern. There is strong autocorrelation. And this makes sense because each observation now contains all of the previous observations, which increases the lag correlations. Now, this heavy linear dependence can be seen as a spike in the first lag of what's called a partial autocorrelation function. To look at that plot, just use PACF. In this lesson, I introduced you to a few new plotting tools that are useful when analyzing time series data. In this lesson, we will be talking about decomposing the different movements of a time series into a trend, seasonal, and random component. So let's load some example data from the ASTSA package. Install the package, and then I'm going to load that package. And lastly, we're going to load some data, which is called JJ, and it's coming from this package that we just installed. Now this data is the Johnson & Johnson quarterly earnings from 1960 to 1980. Notice that the series is not in a single vector, but split by quarter. We can take a closer look at the index by using the index function on this series. R recognizes that each column is a different quarter of the year, so when we plot this data set, it will look fine. This data looks exponential and seasonal. Let's quickly plot the lag of this series. Now we can see more of a straight trend. What about the lag dot plot? So this looks very interesting. You can see how the returns are trending upwards, but there are some seasonal variations, which in this plot just look like cycling. There's a very nice function called STL, which decomposes the time series. So let's create a new variable, decompJJ, which is going to be the decomposition of the dataset. We also need to set an argument called s.window, and we can use tab completion to get a little more information about it. And we're going to set s.window to be periodic. Now, by setting s.window to be periodic, the function will find the seasonality around the average of the series. When we look at the decomposed version of JJ, we'll now see the different components: seasonal, trend, remainder. Let's see what a plot of this looks like. We can now see the seasonality, trend, and remainder in the plot. The quarterly returns tend to get more wild as time goes on. We can adjust for these higher swings at higher returns using the logged version of the dataset. Now let's plot it again. Now when we look at the remainder, you can see that it doesn't tend to increase over time, although it does cluster in certain parts. We also have a straighter trend. In this lesson, we talked about the STL function and how it decomposes a time series into a trend, seasonal, and remainder component. A very useful tool when there's a periodic change in each season. This will allow us to find the magnitude and be better prepared for the future. Now let's discuss different ways to filter out the noise that comes with many time series objects as a way to figure out what significant trends exist which can drive consistent predictions. The first function we'll look at is Holtz-Winter, which fits an exponential smoothing model to a time series. So first let's load the JJ dataset, which comes from the ASTSA package. And the data set is quarterly earnings for Johnson & Johnson from the years 1960 to 1980, split up by quarter. I'm going to create a new variable using the Holtz-Winters function with the data set as an argument. Let's see where that function exists. It's Holt-Winters, not Holtz-Winters. So let's try that again. When we look at that object, we're going to get a few different attributes, including smoothing parameters, different coefficients, and we can plot this object. Now the black line is our original series, while the red line is the smooth series. So it's a pretty good fit for the most part. Now we can also predict what will happen in the future using the predict function on this Holt-Winters object by entering how many steps ahead we want to predict using the n.ahead argument. So I'm going to create a new variable called forecastJJ, and we're going to use the predict function. With our Holt-Winters object, I'm going to set the n.ahead argument to equal 12. So we're going to be predicting 3 years in the future. Now we can enter both the model and prediction as arguments into the plot function, and it will line them up very nicely. So this dashed line is where our observations begin and where our prediction into the future starts. You can see that it's probably pretty accurate. We won't know till we get that data. We can also add confidence intervals into the predict function by adding a couple different arguments. One of them is prediction.interval. We're going to set this to be true, saying that we want the confidence bands, and then we have to give it a confidence level, and we'll set that to be 95%. Let's look at the plot again. The model has 95% confidence that the future observations are going to be within these blue bands. And you can see as it gets further away from today's observation, the bands start to widen out. Let's check out another example. Let's look at the cumulative series of some random data. We're going to first turn it into an XTS object. We couldn't find the XTS function, so we need to make sure we load in the XTS package. Now it should work just fine. Okay, so we have a new random data set as a time series. Before, when we were looking at the JJ dataset, we were actually using a class TS object, not XTS, but TS. So to get an XTS object to work with the Holt-Winters filtering, we need to set another parameter called gamma to equal false. So let's give that a shot. Here's how it would behave if we didn't set the gamma parameter for the XTS object. Okay, now let's forecast this series. And of course, forecasting this series is going to be a little more difficult because it won't have such a clear pattern as this Johnson & Johnson dataset. We're going to predict the Holt-Winters filtering on the X dataset, the n.ahead parameter set to 20, prediction interval will set to be true, and we'll assign a confidence level of 95%. And now let's plot the original Holt-Winters series along with our forecast. So this is our cumulative random series. You can see at time 500 that that's when our observations end and our prediction begins. And the confidence interval for that prediction widens out very quickly. And that makes sense because it's a pretty random data set, although recently we can see that there's a trend going up. So that much we can be confident of. In this lesson, I gave you an introduction to Holt-Winters filtering, which can be very useful for seeing how confident you can be in your future predictions of a data set. In this lesson, we're going to be talking about how to apply rolling functions to a time series. And that can include something like a rolling average or a rolling range. So let's first explore the roll mean function. And first, I'm going to create another cumulative series of some random data. So we came across an error because I put a parentheses in the wrong location, and I actually ended up having an extra one at the end. So I'm just going to fix that. We now have a time series with 500 observations. So now let's try the roll mean function. I'm going to call this variable rmx. And I'm going to be setting a few different parameters. First one is k, and that's sort of the width of the window that you want to look at. So it's going to be giving you the average of 50 observations at every given time. Now we set the align argument to be right. And this means that at each observation, we're going to calculate the mean from the past k observations. So the align argument can also be set to be center or left. If it's left, it will take the future 50 observations and give you the mean at that time. If it's set to center, it will give you 25 observations from the past and 25 observations from the future at each timestamp. Now let's plot our original time series x, and we're going to add some lines to it using the roll mean function. So we'll do a rolling average on x, and we'll set k, let's start with 100, and we'll throw in 200 in a minute. And we're going to set a line to equal right. And lastly, let's set the color to be different. So we'll set the color to be blue. And we now have our first moving average on this graph. You'll notice that for the first 100 observations, there is no rolling average. And that's because it will produce NAs until there are at least 100 observations available to calculate the mean. Now let's also throw in k equals 200. We should see a more smooth trend, and we'll set the color to be green. Now let's start with a fresh plot of x, and now we're going to do a rolling max function. And here you can see the rolling max. Now there's a more general function for applying rolling functions called roll apply. So let's take a look at that. So the function works like this. I'm going to assign a variable, rmx, which is going to be a rolling mean, but I'm going to show you how to do it using the roll apply function. So it's very similar to the rolling mean function. You have the data that you want to apply the function to on a rolling basis. You have an argument called width, which is just like the k argument in roll mean. And then we also have to set which function using the fun argument. And of course, the align argument. Now, if we want to use a different function, like the rolling standard deviation of x, for the fun argument, just set it to be that function name, SD. Now let's look at the number of rows for our data set. We know it's 500. And if we look at the number of rows for one of our roll apply objects, we'll see the same thing. So when you look at that object, and it's kind of long, it's going to produce a bunch of NAs at the start, because at each observation, there were not 100 observations prior to it for it to be able to calculate what we're looking for. I'm going to use the merge function to merge our original data set, the rolling mean of that data set, and the rolling standard deviation. You'll notice, of course, we have NAs for rolling mean and rolling standard deviation for the first 100 observations. So why don't we plot the first column of that data set, and it's going to be the original time series. Next, let's add some lines, and we're going to look at the rolling mean. We'll set the color to be blue. Now we're going to add lines again, and the data we're going to enter is going to be the rolling mean plus 2 of the rolling standard deviations. And then we're going to do the same thing, but we're going to subtract 2 of the standard deviations. So putting all this together, we have created a famous chart tool called Bollinger Bands, using 2 times the standard deviation of the rolling average. You can customize many tools and filters like this using the roll functions, and they're very helpful for analytics. In this lesson, we're going to talk about how to set up and analyze simple autoregressive moving average models, which are a very popular tool in time series analysis. Before we begin, let's create a couple random data sets. So I'm going to create a cumulative series of random data, but I'm going to add it to the number 80 to sort of give it a base price that it's going to start with. Capitalize the P in my variable name, price. So here's our fake price series. So this can be a price series for any good or service. It could also be daily temperatures, number of items sold, etc. The list of possible time series is really endless. Now the plot shows us that the time series is not very stationary because it has a changing average. For an ARMA model, we need to give it a stationary time series, otherwise there will be a serious bias in the model. So we're going to create a new series called price change. And we're going to apply the diff function, which is going to difference the series of our price series. Now the changes are random and bounce around 0 since we used our norm to create the variable. This means that we want a difference parameter of 1 for our ARIMA model. Now I'm going to introduce the ADF.test function, which runs an augmented Dickey-Fuller test to see if this is accurate. So we're going to run an ADF test on our as.numeric price series. Let's find out where that function exists. We can load that package. Let's try the double question mark. It's in the T-series package, so we need to make sure we have that installed, and we need to load it. The price series is not very stationary, as we're left with a high p-value. we'd want a low p-value, something below 0.05, to say that it's stationary. Now, if we run the same test on our price changes series, we'll get a little different result. So we received another error because we know that there is at least one NA in our price change series. Whenever we use the diff function, the first observation is going to have an NA. So I'm going to wrap that inside of an NA.omit function. This looks much better. Our p-value is now 1%, and we can safely say that this series is stationary. And also, I used the as.numeric on the time series to remove the timestamps and get faster results. So now we know we will want a difference parameter of 1 in our ARIMA model. So let me show you how to construct that ARIMA model very quickly. So we're just going to assign it to the variable model1, and the function ARIMA uses a couple arguments. Most importantly, the data set that we want to explore, and then an argument called order, which takes in a vector of 3 numbers. The order argument tells the function how many orders of autoregressive terms, how many differences, and how many moving average terms the model needs to include. And when you look at the model, it's going to give you the coefficients for each of the orders of autoregressive and moving average terms after it's already differenced the series. And if you use the summary function on the model, you'll see that it will output for you all the different attributes of that model. Now let's create the same model again, except we won't throw in a difference term. I accidentally overwrote model 1, so I'm going to re-execute the line to create model 1 using the order of 1, 1, and 1. And then for model 2, we're going to use a 0 for the difference term. The AIC between the two different models, 560 for the first one and 570 for the second one, are roughly the same, and the AIC explains how much information the model is capturing. You can think of that as the quality of the model. Another thing to notice between these two models is that for the first one, when we difference the time series, both of our coefficients are very statistically significant, the autoregressive term and the moving average term. However, when we don't difference the series, the autoregressive term stays significant while the moving average term changes quite a bit. So in this lesson, we discussed how to create an ARIMA model using the ARIMA function. It's pretty straightforward and simple, and there also exists a function called auto.arima, which will help you find the most significant order to use for the ARIMA model. And that comes from the forecast package. In this lesson, I'm going to give a more in-depth talk about logical operators and if statements. So we have talked about Booleans and logical operators in previous lessons, but let's quickly review them before we talk about if statements. So a Boolean, again, takes a value of true or false. Numerically, these are expressed as 1 and 0. So here's some code I prepared ahead of time that you'll be able to find along with the video. I'm just going to run the first couple lines. So we now have a Boolean vector called boo, and when we run an as.numeric on that vector, it returns a series of zeros and ones. We can also do some simple logical statements. If I create a simple numeric vector of the integers 1 through 10, we can compare them to different numbers using logical operators, such as the less than sign, greater than or equal to, and so on. For these lines, I'm comparing one element from the vector to a number and seeing if it's less than 5. Now we can also subset with simple logical statements. So I'm going to subset my numeric vector and pull out only the numbers which are greater than 8. The first line only returns 9 and 10. Greater than or equal to will return 8. Then if we use an exclamation point outside of that logical question, it's going to return the opposite. So it's going to give me everything that is less than 8. We can run multiple logical questions inside of a subset. In this case, this vertical line here is an OR operator. We're going to be looking for all elements in that vector that are greater to or equal to 8 or less than or equal to 3. Now, these logical operators are essential for if statements. An if statement evaluates a condition, and if that condition is true, it returns the first expression. If false, it returns the second expression. So you can see sort of a general setup for that if statement here in the code. If this condition is true, we're going to do this. Otherwise, let's do this other part. So here's our first if statement. If the first number in the number vector is greater than 5, we're going to print greater than 5. Otherwise, we're going to execute this other code. When we run that code, it's going to return not greater than 5 because we know that the first element of the numeric vector is 1. So the if statement doesn't need to be in one line of code. They can extend however far they need to, and in fact, this is a very conventional way to write an if statement because it's easier to follow. So look at this next if statement, lines 25 through 30. We're going to be creating a variable called state, and we're going to assign it the value of a character string, which is Illinois. So now you can see the first sort of general layout of an if statement. We start with the if condition, and we open some curled brackets. Then we set the first line of code, if that statement is true, by itself, close the bracket, state else, and then start the next bracket for if the if statement is false. So when I run this code, by highlighting it and clicking on the run button, it's going to set the variable region as Midwest. Now, if we want to extend this and have other conditions inside of this if statement, we can use else if instead of else for a nested if statement. We can see that in the next example. So now, if state equals Georgia, we're going to set region to be Southeast. Otherwise, if the state equals Washington, we'll set region to Pacific Northwest. Otherwise, let's set the region to be Midwest. Now, an if statement can be even simpler. For the if statement, you can have it return some code if the condition is true, and you can have it return nothing if the condition is false. You don't need to use an else condition. For example, we still have our number vector. Let's say if the fifth element is greater than 4, we'll have it print that this number is greater than 4. And when we run that, it's going to print that because we know that the fifth element is 5 and greater than 4. Now, if we set this to be the first element instead, it's not going to execute anything because that condition is not true, and there's no else statement to tell it what to do if the condition is false. Now, we can also use what's called a vectorized if-else statement, which is much more powerful and much quicker as well. So I'm going to create a vector called states, which is going to include Illinois, Georgia, and Washington. For the if-else statement, it works as the following. We first specify the condition, then we specify as the second argument for the if-else function the expression or the code that we want to run if true, and then lastly, for the third argument, we enter the expression that we want to run if it's false. So for this one, I'm actually nesting an if-else statement within an if-else statement. If the states equals Illinois, it's going to return Midwest. Otherwise, if the state equals Georgia, Southeast, otherwise Pacific Northwest. So the reason this is called a vectorized if-else statement is because it's going to apply this logic to every element in that vector. So now when I look at my regions object, we'll see 3 different elements, which is the same length as the original vector that I put into that if-else statement. It is fast and you should use it when you can. Otherwise, normal if statements like above should work just fine. When setting up these evaluations, start with the condition and make sure you understand when it is going to be true and when it will be false, and make sure that it captures the differences correctly. This is a great way to say, for this characteristic of this object, I need it to behave this way. If it's different, I want something else to happen. So in this lesson, we reviewed some earlier topics about logic in R and how to apply them to if statements, which we can use to get different outputs depending on the state of the object. So don't forget the 2 different ways we can set up the classic if-else statement, or we can use an if-else function in a vectorized form. In this lesson, we are going to start talking about loops. Apply functions are considered loops, for they loop through each column of a matrix or loop through each item of a list. There are many kinds of programming loops, but for now we will start with a for loop. A for loop works by looking at each element in a vector and running one iteration of the code within that loop, also known as the inner code, for the number of elements in that vector. So let's start with a very simple loop. We're going to run a print statement for every iteration in a vector of numbers. So you can see right here at the start of this code, which will be included with this video. To start a for loop, you type the word for, and then inside of parentheses, sort of like with an if statement, you have to say for a variable in some range. Very simply for this one, I'm going to be using the integers 1 through 10. And then for each iteration of that range, it's going to print a quick statement saying the number is n. When I execute this code, you'll see that it runs through 10 different times. Now we can add more code within the curled brackets. So it doesn't need to be just one line of code. It can be a very long set of code. So in this next example, we're first going to square whatever our iterator is, and then print what that squared number is. So the squared number of our iterator is 1. Once the iterator reaches its last value of that vector, 10, it just stops. Now we can even add an if statement inside of a for loop. So in this example, when the iterator equals the last value of the vector we're iterating over, which is 10, we're going to print that the loop is done. It's finished calculating. And here in the console, you can see that it worked just fine. Hopefully at this point, you're starting to get a better idea of the extent to which you can use loops and if statements. They can be nested within each other in many different ways, which can often cause problems. Keeping the brackets straight can sometimes be a challenge. Luckily, RStudio makes it easier by letting you know which bracket each one is paired with. For example, on line 18, when I put my cursor around this curled bracket, it's going to show me which one it's paired with, and we can see that it's all the way up here at the start of the for statement. If there are too many brackets, you will see an error message, and I'll show you that right now. In this example, lines 20 through 23, I purposefully added an extra bracket so we can see how it behaves. So the error is pretty simple to read. It just says that there was an unexpected bracket. And if you source the code, instead of just running those few lines, it will actually tell you at which line the error occurs. So on line 23. Now in this example, lines 26 and 27, I took out the ending curled bracket. So when you execute code like this, it's going to give you a plus sign in the console. And that is asking for some more code. It's basically asking you to finish off the bracket. So for this example, all I have to do is enter in a curled bracket, and then it will run just fine. Now, another important aspect of the for loop, or any loop for that matter, is the next command. This command allows you to skip certain iterations of a loop. So let's take our simple example and have it skip the iteration whenever n equals 5. So here's the code, lines 30 through 33. As we go into each iteration, we're first going to evaluate what that iterator is. Once it equals 5, we're going to skip to the next iteration. So when we run this code, you'll see that it prints every number except the number 5. And lastly, if a condition becomes true within a loop, we can also break out of the loop, which stops the loop from iterating entirely. So in this example, when the iterator equals 5, we're going to break the loop. It prints the first 5 numbers, and then it stops. This time it printed the 5th number because I set the break condition to be after it prints that iteration. In this lesson, we talked about for loops, and for loops are rather simple, and they execute the inner code for every item in a stated vector. We can control which iterations we either skip or end the loop on using the next and break commands. In this lesson, we're going to talk about while and repeat loops. A while loop executes some inner code until the condition being evaluated at each iteration becomes false. As such, there is a danger here for building an infinite loop. For our first example, let's set n equal to 1 and run the code n equals n plus 1 while n is less than 10. Once n equals 10, the loop will stop as n is no longer less than 10. So we first set our iterator to equal 1. And then the code itself looks very similar to a for loop, except instead of having the word for, we have the word while. We can run this code, and it's going to print the number n up until 10. Now it doesn't print the number 1 because we set n to equal 1 first, and before we print the number, we add one more to it. To fix this, we could set n to equal 0, and now it's going to print 1 through 10. So here's an example of an infinite loop. We're going to set n equal to 1, and we're going to say while n is less than 10, we're going to print n, the number, and the system time. So you can probably see what the issue is right away. We're not actually making any changes to our iterator n inside of the loop, so it's always going to be less than 10. So let's run this infinite loop, and you can see how R handles it. It's still printing, and the reason I put system time in there is so you can see that it's still going and going and going. And it's going to keep doing this until we hit this little stop button on the console. The stop button will cancel any code that's currently running in the R console. So it's been running for 20 seconds now or so, and I'm going to stop it. Now we can add code internally to stop the loop automatically. So in this example, I'm not going to be changing the iterator at all, so this condition is always going to be true. But I can set a break condition if the difference of the current time minus the time before the loop started is greater than 10 seconds. So let's see how that behaves. So it's going to iterate through this loop for 10 seconds. The while loop's not going to stop because n is greater than 10. It's going to stop because it reaches a break condition. A repeat loop will repeat a set of instructions until a break is specified. So in this simple example, I'm going to be setting an iterator to equal 1. And then for the inner code of the repeat function, I'm going to be setting n to equal n plus 1. And we're going to print the mean of 100 random numbers until n equals 100. And then it's going to break out of the loop. So it runs very quickly, but it ran basically 100 iterations of that code, and then it stopped because n now was greater than 100. So in this lesson, we talked about while loops, infinite loops, and how to avoid getting stuck in one, and we also talked about what a repeat loop is. In this lesson, we're going to talk about appending loops in R. We can use a loop to add an element at each iteration to a vector. This is often very useful, and there are ways we can significantly increase speed, which may be a factor with huge datasets. So let's set up a simple for loop that will return the mean of a random series. We're going to iterate n through the numbers 1 through 1,000. And at each iteration, we're going to print the mean of 100 random numbers. So you can see that it ran pretty quickly. The question is, how can we get the 1,000 means into one vector? When we execute this code, it's going to output a bunch of different numbers for each iteration, but they're really not together in any way. We can see that we're left with two different objects in our environment, n and also m, which is the most recent mean of random numbers. If we want to get all of these different means from each iteration into a vector, we can do it two different ways. The first way is to create a null object. So I've created this object means, which is basically nothing. It's a null object. Then for each iteration of the for loop, I'm going to change means to be an rbind of means with the recent m object. So let's run this code, and then we're going to plot the means vector to make sure that it worked just fine. We can see that it has. It's given us 1,000 different iterations of the average of a bunch of random numbers. So what's going on here? Well, every time we execute an iteration of the loop, we capture the mean and attach it to the rest of the means that we have been building up. At the first iteration, however, we only have one mean, and we need to be able to attach it to something. We were able to attach it to that null object. So after the first iteration, means was no longer a null object. It actually had some information. Now, another function that is helpful for diagnostics is called system.time, but lowercase s and t. This function will tell us how long it takes to execute some code. So let's make the range of our counter to be even bigger. So we're first going to set means to be null on line 13 here. And we're going to wrap our for loop inside of the system time function. And we're going to set our iterator to reach a much higher number, this time 20,000. I'm going to execute this code. It's going to take a few seconds to run because it's a rather long vector. And then the system time actually returns how long it took in seconds, 5.3 seconds. Now we can speed up this process by adding what's called an injection step. Instead of setting a null object and appending to it at each iteration, we can create an empty vector that is the same length as our desired output. So this line of code, in line 21, I'm setting means to equal an empty numeric vector which has a length of 20,000. Then each time I iterate through it, instead of appending two different objects together, I'm going to be setting the index of that 0 numeric vector to equal the current mean at that iteration. So let's see how fast this is. You can see that it's much, much faster. It took 3/4 of a second versus 5.3 when we're using the appending method. So there are simple steps like this that can be taken all over the place to speed up your computation. We have mentioned a few in previous lessons, such as using the core data function on large time series objects, or using if-else and other vectorized computations. Using system.time will help you decide which way to set up your code. In this lesson, we discussed how to use loops to build new vectors or datasets by appending the loop calculation in different ways. Generally, it's better to create vectors or data sets using this injection method because it's faster, but it's not always necessary. So with the attached code to this lesson, I've also added a few more examples that you can go through and test yourself. In this lesson, we're going to talk about how to create your own functions, and these are called user-defined functions. So there's a general setup, and you can see it up here in these first few lines of the example code that's attached with the video. We first give it the function name, and then we assign it the function creation code, which includes the word function, followed by a list of arguments in parentheses, which is then followed by some curled brackets, which has the code to be executed on the arguments, and it finally returns a certain object. So why don't we go over a real simple example, and this function is just going to add two numbers together. First, I'm naming the function f1, and then I assign it as a function with two different arguments, x and y. And then the function is going to return the sum of those two numbers. Now, this return part is very crucial because this will output the results from the function. So why don't we run this code and we'll see how it looks. So now if I want to use the function, I simply type the function name f1, and then I put the necessary arguments into parentheses. So I need to specify two numbers for this. And let's say I try 3 and 4. And it returns 7. So we know it works well. Now we can even add error handling into our own functions, and this is actually very good practice to do. For example, if the arguments are not what they're supposed to be, so that the functionality would not work properly, then we need to produce some sort of error message. So now, using the same function that just adds two numbers together, I'm first going to make sure that they're both numeric. If x is numeric and y is also numeric, then the function is going to return the summation of those two numbers. Otherwise, if either one of them is not a number, it's going to print not a number. So now we know it will work with two numbers, but if I, for instance, throw in a character, it's not going to work. Now the functions I've showed you so far return just a single number, but what if we want to return multiple variables? In this new function, we're going to use different operators on the two numbers. So to return a list of elements, and in this case, a summation, a subtraction, multiplication, and division, then we're going to need to first use the C function to put them all together into one object. So now when I enter in two numbers, let's say 5 and 7, it's going to return the summation, subtraction, multiplication, and division. Now in this next function, instead of using return, we're going to use list, and it's going to return the list for us. And in this case, it's returning the object as a list. Now let's see what happens when we use vectors as an input. My x vector is going to be the numbers 1 through 5, and y vector is going to be the numbers 6 through 10. And I'm going to try to throw them into our f1 function and see how it behaves with these vectors. So you can see that it actually worked just fine with vectors. I can use this function as a vectorized function. It returns a list with 4 different components, one for each of the different operations that I want to return in the function. And then for each component, it's returning that operation for each element in the vectors. You'll notice that for the subtraction one, they all equal -5, because I'm subtracting 6 from 1, 2 from 7, 8 from 3, and so on. Now, if you want to examine the function code, just type the function name with no parentheses, and it will print for you in the console what the code is. Now, we can get the arguments by using the formals function. In this function that we've created, there are two arguments, x and y. Now, another important aspect of creating your own functions is setting defaults. We can set defaults just like this. When we list the arguments, when we're creating the function, all we have to do is say, for example, x equals 1 and y equals 1. Now, for this function, we can execute it without any arguments, and it will automatically set x to equal 1 and y to equal 1. The arguments function works sort of like formals. It basically just shows you what the arguments are and if they're set to be any defaults. So in this lesson, we talked about how to create your own functions. This can be very important because you will not always find the function you need for certain conditions. Now let's talk about how to debug a function. Sometimes when you're trying to use a function, you'll get strange errors and you're not really sure why. It's good to know how to debug a function just in case the arguments that you're entering into the function are causing the error. Or if it's a user-defined function, one that you've created, this will help you step through and find any errors. To step through the code of a function, we use the debug function. So in this first example, we're going to debug the mean function, which just produces an average of some numbers. When you use the debug function, it basically flags that function. So next time you execute that function, it knows to debug it. So after flagging the mean function, I need to execute the mean function, and then it will step through. So I'm going to calculate now the mean of the numbers 1 through 10 in debug mode. Now, as soon as you execute this line, you'll see that it's telling us that we're in debug mode, and we're now at a browser inside of the function. So the first step in the debugging is to produce all of the code in the function. So it's basically saying, these are all the different steps we're going to walk through. And as you press enter, it's going to run through different pieces of the code. So this is the first piece of the code that it's going to run through. It's going to do some checks on the vector that we're throwing in. And if they're not numeric or logical, it's going to produce a warning sign. Now, at any time in the code, we can actually call these different objects that it's working with, so we can see exactly what's going on. If the argument na.remove is set to be true, then it's going to remove all the NAs from X. Right now, my X vector has no NA, so it just skips past that part. Now, there are a couple helpful commands to know when you're in this sort of browser debug mode. Now, the first one is enter. Every time I hit enter, we're going through another line in that function. If we type a lowercase c and press enter, it's going to run the rest of the code. But if you are in a loop, it will run the rest of that loop and then bring you back out to the next level of the code. Lastly, a capital Q will quit the debugging mode and it will stop executing the code. Now, when you're finished debugging a function, you need to use the undebug command to unflag the function. Now, browser is another way to step through code. You can't really use the browser in a function, but you can use it inside of a loop or any other parts of the code. So in this example, I'm going to be going through a list of numbers using a for loop, and we're going to be attaching those numbers to an empty numeric vector. At each step, it's going to pause and allow me to inspect the code at that time. So I'm going to run this loop. It goes through, executes the first part of the code, it sets I to be 1, and then it pauses. So at this point, I can inspect my numbers vector and see if there have been any changes. And at this point, they're still all 0. As I hit enter and I keep going through different iterations of that loop, it's going to be appending or changing the numbers in that 0 vector. So I'm going to hit enter a few times. We'll see that we've now built up the numbers 1 through 4. So this is a very, very helpful tool, and I use it very frequently. Especially when you first build a loop of any kind, it's really helpful to use just to make sure that it's doing what you want. Now you can also use these browsers inside of a conditional statement. Let's quit out of this current browse. Now I'm going to run this new code that has a browser inside of an if statement. So once I equals 6, it's going to pause. Now we can see where our iterator is at, 6, which is correct. And we can see what our numbers vector looks like. We can set up R to call the browser function if any error occurs when programming. We would use the options function and set error to equal browser. Now, you should really only do this when you are experiencing errors. It has undesirable side effects if it's left turned on, so it's important to switch back after you're done with your debugging. And lastly, let's look at an example of using traceback, which comes from the InsideR.org website. So here's a simple function called foo, and it's going to print whatever I put in as an argument. And lastly, the bar function, which I call again inside of the foo function, is going to try to add x, the argument I'm entering in, with a variable which does not exist. So then when I run foo2, it's going to print the number 2 and try to add 2 with something that doesn't exist. And we can see we receive an error, just like we would expect. That object does not exist. So then we can run the traceback function, and it will tell us where the problem occurs. It occurs at the second step, when it tries to run bar x. In this lesson, we talked about how to debug functions using the debug set of commands, the browser commands, and also traceback. In this lesson, we're going to talk about what a recursive function is. So the first example for a recursive function I want to show you is a function that calculates a Fibonacci sequence. This function is recursive because it calls itself within the code. So in this example, we throw in a number and it calculates the Fibonacci sequence up to that number of digits. In the code, it actually calls itself by subtracting 1 from that number, and then it keeps doing that again and again and again until n equals 0. So I'm going to execute this code, and we're going to look at a couple outputs of the Fibonacci function. Recursion can be kind of slow, so I'm going to use the system time function on the Fibonacci function going out to 20 digits just to see how long it takes. So you can see that it's still running. Before, when we ran the Fibonacci sequence up to 10 digits, it was a little faster, but as we keep adding recursions or iterations, it gets much longer. It took 10 seconds to run that. So this sort of recursion is rather slow. It should only be used when performance is not compromised and when coding this way is natural. Now here's another version of the function that is much quicker. It only returns a single value and doesn't bind together groups of objects like in the previous example. And because it's not binding together groups of objects, we know that that works a little faster. So now let's calculate the system time on this new Fibonacci sequence. 0.14 seconds versus the 9 seconds before. But there's a big difference now. It only outputs a single number instead of outputting the whole sequence. Now here's another example of a recursive function, which prints a factorial. This one is rather fast, and part of the reason is that it's only returning a single number. If you want to set up recursion in your program, avoid using functions like c, rbind, or cbind. Returning single numerical values is much faster and won't so easily cause a crash. This lesson is going to be very short, but I just wanted to give you some more information about how to save information as different files onto your computer. So we can save any object as an rdata file by using the save function. I'm going to create a matrix of numbers 1 through 12. I'm going to use the save function, which needs 2 arguments, the data object that we want to save, and also the file name. So when I run this code and I go to my Files tab in RStudio, I'll now see that we have this new object called x.rdata. Now I can remove all of the objects from my workspace using the rm function and setting list to equal the ls function, and then I can load that rdata file by using the load function and simply entering in the name of the file. And so now we have our x back in our workspace, and it looks exactly the same as it did before. We often need to output data in a CSV form for others to reference. So why don't we load the mass package, and we'll load the Cars93 dataset. Now to write a CSV file, which is easy to work with in programs such as Excel, we use the write.csv function. It takes 2 arguments, the data that you want to save as a CSV, and the file name. When we're using functions like these, they're putting them in our current working directory. If you want to put them somewhere else, you can specify a full path. And now in the Files tab, we can see the Cars93 dataset output as a CSV. And just like before, if I clear my workspace, I can load the CSV file by using the read.csv function. Now you can also write directly to other statistical program file types using the foreign package. So if you want to get the foreign package, just run this line of code. So in this quick lesson, we just talked a little bit more about how to save and load different file types. This can be very important, especially as you're working and you need to save certain parts of your environment.